Hello and welcome back. Today's lab we'll be talking about the HR diagram, and let's get started. In this lab, students will learn about HR diagrams, how they are done, the information we can obtain from them, and we'll be able to do one on our own using the methods that we learn in the STARS lab to obtain information about stars, such as absolute magnitude, distance, temperature, and luminosity. Also, the students will learn the process how astronomers calculate the temperature of a star by using real data from CTMO. A little bit of background. In lab number 6, the STARS lab, we learned about one of the most important discoveries in understanding stars, the concept of star luminosity, and how it relates to our own sun. Luminosity is a quantity that depends on the star itself and not on how far away it is from us. We call this an intrinsic property. Intrinsic, right? So it belongs, or it's a property from within itself, intrinsic. And luminosity, if we remember from the example that I gave once before, when we compared the energy that was being output from a bonfire to that of a single candle. Though if you put a candle up close, it may appear in brightness brighter than a bonfire that's set really far away. But the energy that is output, or its luminosity, would be much greater than that of a candle. So luminosity is a quantity that depends on the star itself, right? And not how far away it is from us. If you combine the information about how bright a star appears to be with knowing the star's distance from Earth, you can calculate a star's luminosity and its absolute magnitude. If you recall, a star's absolute magnitude is the apparent brightness the star would have if it were at a distance of 10 parsecs away. In the previous lab, we also learned that the luminosity of a star is directly correlated to the star's temperature. However, we did not discuss the role that the star's size or mass might play in all of this. The fate of a star from its inception to the moment of its death depends entirely on its mass. The life cycle of a star will span anywhere between millions to even billions of years. The color and temperature of a star will tell us whether the star will live millions or billions of years old. There are two main types of stars in terms of their mass. We have low mass stars and high mass stars. Low mass stars and high mass stars. Now, we will see a chart now that shows these two things. And I'm actually in the way, so let me get out of the way. The low mass star starts from a stellar nebula, as well as the higher mass star. They both start from a stellar nebula. This is a collection of dust and gas, and then starts clumping together. We will take the lower mass path. If the stellar nebula clumps up, it's a lower mass. It'll become an average star. It'll become a red giant. It'll become a planetary nebula, and in which it loses all the outer shells of the star, of where it was going through this fusion process, and then you're just left with this little thing called a white dwarf. Now, if we follow the path of a higher mass star, it becomes a massive star, a red supergiant, in which case, rather than losing its outer shells due to no longer being able to keep up with any fusion, or there's not enough gravity to keep it together, gravity will win in this process, in which case the star then goes supernova, and depending on its mass, the core remnants will either leave a neutron star or or a black hole. Now, we found a really cool video by the Institute of Physics called The Life Cycle of Stars. Now, rather than me showing it here, it would be best if you pause this video and watch the life cycle of stars. Here, I put the address, but I'll also make sure that I put a YouTube card so you can just click on the link and it'll send you straight to it. When you're done, come back and we'll finish the rest of the lecture. Welcome back. So, low mass stars. A low mass star is identified or is defined to be one whose mass ranges anywhere between approximately 13 Jupiter masses, which is the smallest mass a star can be to undergo nuclear fusion, to all the way to a few solar masses. All right. So, this is an important number. A low mass star. 13 Jupiter masses is the smallest mass a star can be to undergo the nuclear fusion. For a star to be born, a massive amount of gas is required to form it, and the mass of the gas that gas generates a tremendous amount of gravitational pressure that makes the atoms within the gas fuse together in a process called nuclear fusion. So we have to remember that 13 Jupiter masses to start the nuclear fusion process. Here, there's a graphic that shows what's happening. We started off with hydrogen gas from the stellar nebula. Then from there, once we have that the clump of gas to 13 Jupiter masses, the fusion process starts, where we start going from hydrogen to helium. And in that process, there's this excess pressure that's pushing outwards, but gravity is pushing inwards. Low mass stars. Normally, the atoms involved in the formation and the production of a low mass star's power throughout most of its lifetime are hydrogen, with the symbol H, or helium, and the symbol is He. That's the things that we're looking at here. You see, it goes from H to He, and the bright yellow part, which is the outer shell, as we call it, is mostly hydrogen. Low mass stars will spend most of their lives fusing hydrogen into helium. So low mass stars will spend most of their lives fusing hydrogen into helium. This is really important. Maintaining a relatively steady size, temperature, and luminosity until almost all of the hydrogen is gone. Because of this process of fusing hydrogen into helium happens during the longest phase of the star's life, the stars in this phase were dubbed the main sequence stars. Eventually, as hydrogen begins to run out, the core of the star will shrink and get hotter, making the remaining hydrogen burn even faster and pushing the outer layers of the star outwards, making the star to grow much larger size due to the vast amounts of energy released from the accelerated nuclear fusion process. As the outer layers expand, they cool, thus become more and more red, and the star slowly but surely evolves into a red giant. For example, here is our sun. Then we have the smallest Kepler red giant and the largest Kepler red giant, and we can see their temperatures. And look how red they are. The star can remain as a red giant for up to 1 billion years, after which, with almost all the hydrogen gone, the core gets even smaller and hotter. The star is so hot at this point that it is able to now fuse hydrogen atoms into heavier elements, such as carbon and oxygen, amongst others. Since the star had been making helium for a long time while it was a main sequence star, it has a new-found source of fuel to stay alive in helium. As it burns its helium into heavier elements, the star begins pulsating as it runs through its final energy reserve, slowly becoming smaller, hotter, and bluer until much of the helium has fused into larger nuclei. Once the core is predominantly carbon and oxygen with just a shell of helium around it, the shell of hydrogen on the outer part of the core, the the core will collapse, but the star will eject once more its outer layer, making the star grow even bigger in size for a short period of time, and finally leaving behind a very hot, bare core about the size of Earth. As it gradually cools down, the core will contract even further until the remains become what is called a white dwarf star, and thus ending the life of the low mass star. Now, high mass stars. High mass stars are much more massive than our sun and are quite different from low mass stars. Things start out normal with a huge gas cloud collecting under the influence of gravity. It's simply that this cloud will be much larger than those that form the low mass stars, so it will contain much more mass than the low mass stars. More mass means more gravity, which means that the force pushing inwards is much stronger and the star gets much hotter. A hotter temperature means faster fusion, which generates greater outward nuclear fusion pressure to counteract the greater inward pull of gravity. This will result in a main sequence star that is hot, bright, big, and blue. This is where things start to deviate from the low mass stars. High mass stars are much hotter and burn their fuel much faster than the low mass stars. That means that they use up all the hydrogen in their core in around just a fleeting 100 million years, or even 10 million years if big enough. The core of a high mass star continues to compress. It gets much hotter than the core of the low mass star, and it continues to fuse helium nuclei to form carbon and then oxygen, then neon, then silicon. Each heavier nucleus being relegated to a smaller and smaller region of the core that is hot enough to fuse it. All the way at the center sits the heaviest element that can be fused within a star: iron. As this occurs in these different layers, each performing a particular type of fusion until no fuel remains, the star is left with a core of iron nuclei that are so stable that further fusion can release no more energy. At this point, gravity wins the fight. The star collapses within a single second, the outer layer bouncing off the core and triggering an explosion, thus ejecting all the heavy nuclei the star has created out into space. This awesome event, one of the most violent and energetic phenomenon in the universe, is called a supernova. A supernova generates such unbelievable burst of energy that in this brief moment, dozens of elements heavier than iron can be synthesized. For example, here, nickel, copper, zinc, silver, gold, any element with an atomic number greater than 26 is made either in a supernova or a rare event like the collision of two neutron stars or a neutron star and a black hole. One of two things will be left behind. If the core is between around 1.4 and 3 solar masses, the core will not be able to support itself against gravity, and it will collapse with such tremendous force that all the electrons get squeezed into protons such that they combine to form neutrons, and the shockwave from this event is what triggers the supernova. Now it's important to remember these numbers: 1.4 and 3 solar masses. They will generate what's called a neutron star. The object that remains is a ball of neutrons bunched up together like one huge atomic nucleus the size of New York City, containing all the mass originally within the core of the star. A teaspoon of a neutron star would weigh a whopping 10 million tons. Now, to make this relatable to us who live here in the Rio Grande Valley, if you have ever traveled down the expressway to get to pass through Brownsville to get into Mexico, um, when the major intersection that you would pass up and there's an exit is Alton Glore. So if you travel down Alton Glore all the way to up until you get to University Boulevard, that is the diameter of what a neutron star would be. Imagine getting the something between, remember the numbers 1.4 and 3 solar masses. So if we get our sun, sprinkle a little bit more sun, and then get it down to the size between Alton Glore and University Boulevard. That's how much mass we're compressing into such a small space. Now, the other option would be if the core of the star was above or around 3 solar masses. Even the outward pressure of neutrons pressing right up against each other is not enough to stop the immense gravity. Neutrons will be crushed together as the remaining mass collapses into a single point of infinite density. The entire mass of the star's core contained within zero volume. This object is called a black hole. Wow. This is a really cool picture. What's really mind-blowing is that the light that you're seeing over the top of that black hole is actually light that's bent around the side of the black hole. Same thing is true from underneath it. So it's not that you're seeing a bubble shape, it's just that you're seeing the other side of the black hole being bent and up towards us. It's really mind-boggling. The HR diagram. It took many years for scientists to understand the life cycle of stars and the process by which they generate energy. A century ago, in their quest to understand how all of this works, scientists gathered a lot of information about stars using astrophotography. The only problem was that this was being done for hundreds of thousands of stars. A century ago, astronomers Hertzsprung and Norris Russell made a graph in which they plotted the star's solar luminosity versus its spectral class or temperature. When they did this, they got a surprise. There was a very strong trend, and this diagram that they made is called the HR diagram after Hertzsprung and Russell. And here it is, the HR diagram. There are a couple distinct features that we can see, and you can see these clusters of stars. Now, this isn't what you would see in the sky. But this is more like a catalog of things that were seen or observed in the sky, not by position, but look at the x-axis. Here, the x-axis shows the surface temperature in Kelvin. Remember, we went over the different luminosity classes, the O, B, A, F, G, K, M, and on the left side we see its luminosity, which is the total output energy. Now, that is actually all we have for today. I'm just going to point out some of the features. They say them on this graph itself, but you see the big line is the main sequence stars, and they have these green lines there that are saying the lifetime of those stars. And on the bottom left of the diagram, we see the white dwarfs. On the upper right, we have the supergiants. And right underneath the supergiants, apart but almost touching the main sequence stars, we have the giants. Now, as always, if you have any questions, make sure you reach out and ask me. I'll be uploading some tutorials and other things that might be helpful in completing all the labs. But I hope you enjoyed this video, and have a great day.